Welcome students, this is lecture number 8 of VLSI design KEC 072. So, we will continue with our broad topic which we have been continuing since last 2 lectures, which is estimation of delay in VLSI logic circuits. Okay. So, today we are going to discuss another model. We have already discussed the RC delay models in our previous lecture, and today we are going to do what is known as the linear delay model, and will introduce the concept of what is known as logical effort. Okay. So, delay as we know is directly dependent on what is known as fan out of a gate. Fan out in very simple terms means how many gates are being driven by a single gate. So, the number of gates being driven basically becomes the fan out of that gate. Okay. Our aim has been throughout to simplify our calculations of estimating delay, because given the complexity and the density of VLSI circuits, it is very difficult to pinpoint something with great accuracy, okay, or to reach at a certain level where you can reach a very reliable value of delay. Okay. So, it is always good to simplify, right, and one of the way of simplifying delay estimation is known as what is known as the linear delay model. I am stressing on the simplicity because almost all of us know about equation of a straight line, and the linear delay model is basically is quite analogous to what a equation of a straight line means, right. We define what is known as normalized delay. It has a very simple equation. Normalized delay is written as d equal to f plus p. In the above equation, d obviously is your normalized delay, p is the gate parasitic delay, the delay when no load is attached. So, if a gate is not driving any other gate, that is what is known as the parasitic delay. F means effort delay or stage effort, and that is basically a measure of complexity and fan out. And the effort delay by itself can be written as a product of two terms G dot H, where G is the logical effort and is a measure of gate complexity, and H is known as electrical effort, which represents gate fan out. So, if I use the equation on the previous slide, D equal to F plus P, and the equation of F which is equal to G H, I can write that a normalized delay okay, if you compare it with the equation of a straight line, which is y equal to m x plus c, right. Y is the dependent variable, x is your independent variable on the coordinate system, m represents the slope of the graph, and c is the intercept on the y axis. If I compare these two equations, I can say that if I plot a graph between d, my normalized delay, and h, which is the electrical effort or representative of the fan out of the gate, I should get some straight line such that the slope of this line represents G, the logical effort, and this intercept here should give me the parasitic delay. Okay. So, this is what basically means, this is what linear delay model is all about, right. As you can see on the slide, I have already described fan out, which is basically number of devices being driven, okay. But that does not take into account which there might be some differences in the capacitances of the gate which is driving and the gates which are being driven. Okay. So, the driver and the load may have differences in capacitance, right, and that is not taken into account if we simply define fan out as the number of devices being present at the load. So, in a better way, the fan out is described as the output capacitance divided by the input capacitance. Okay. So, as I shown on previous slide, if I plot a graph between normalized delay D, this is your D normalized delay, this is electrical effort H, ratio of output and input capacitance, this should give me a straight line. The two straight lines shown on your slide, one is for an inverter, okay, and another one is for a 3 input NAND gate, right. So, the slope and the intercept basically provide you the values of logical effort and the parasitic delay. Right. Now, we move forward and we do how to estimate the logical effort. This is what symbol G is all about. Okay. This is represented by symbol G and it is the logical effort. Okay. And it defined as the ratio of input capacitance of the gate which I am talking about, the gate which is driving further loads. Okay. So, the input capacitance of the driving gate divided by the input capacitance of that inverter which produces the same output current as the driving gate. Okay. So, if you have a logic circuit, okay, that acts as a gate which might be driving multiple other loads. Okay. So, that driving gate, whatever input capacitance it has, you divide that capacitance by the capacitance of a similar inverter. Okay. So, I am saying similar, they are similar in terms of the output current. Okay. So, a particular inverter which must be delivering the same output current as my driving gate, if I divide their input capacitances, I get what is known as the logical effort. Okay. It is a performance parameter, and since it is a ratio of two like terms, it is a ratio of two capacitances. So, it is unitless, it usually has a numerical value which is generally an integer, okay, and it is a performance parameter in a negative way. Okay. So, lower the value of G, the better is going to be your gate driver, right, and if the value of G increases, that basically means that the performance is worsening. Right. So, logical effort basically indicates how much worse a gate is at producing output current compared to an inverter, given that each input of the gate may only present as much input capacitance as the inverter. Okay. So, it is a performance parameter for any digital logic VLSI circuit, right. So, let us see an example, right, how we can actually quantify, because our aim is to quantify the delay in VLSI circuits, and we are discussing the linear delay model for which logical effort is a major component. Okay. So, consider this circuit which is drawn on the slide. This is a basic inverter, it has a PMOS on the top followed by NMOS. The input, being an inverter, it has a single input, this is a 1 bit inverter. So, you have one input A being applied to the gate terminals of the two transistors, and the output is being taken from this joint terminal here. Okay. So, when A goes high, your NMOS transistor turns on, because it turns on at high voltages, and that gives logic 0 at the output, and when A goes low, a lower voltage logic 0, the PMOS transistor gets connected, gets pulled up to the power supply and gives you logic 1 at the output. This is how basic inverter works, right. Now, this, if I want to calculate the input capacitance of this, and if you see these numbers here, I have written 2 here and I have written 1 here. Okay. These numbers basically denote or written to realize what is known as the unit transistor. In the RC delay model, we have already described what a unit transistor is. It has a certain resistance known as R, it has a certain capacitance known as C, and if you want to increase the width of the transistor, if the width is increased by k times, the resistance will reduce by k times as compared to the unit transistor. Okay. So, if a particular transistor has k times the width of unit transistor, it will have a resistance R by k and capacitance k dot C. Okay. And we deliberately try to make the PMOS transistors of higher width, so that they have lower resistance. This is because PMOS is a hole driven transistor, NMOS is an electron driven transistor. Holes have lower mobility as compared with electrons due to physical reasons, okay. And because of lower mobility, a PMOS generally tends to produce lower current as compared to NMOS transistor. And to compensate this difference, we deliberately try and make twice the width of the PMOS transistor, so that it has half the resistance of an NMOS transistor, and that compensates the differences in current. So, whatever input you apply to this inverter, right, it is going to see 3 units of input capacitance, 2 times C from here from the PMOS plus C from the NMOS. This much capacitance comes from the PMOS and this much comes from the NMOS. So, in total it produces 3 times C, where C is the capacitance of a unit transistor. Okay. And if I go by the definition of logical effort, that is the ratio of input capacitance of the driving gate to the input capacitance of an inverter producing the same output current. So, if this inverter acts as a driver for any other circuit, the logical effort for this inverter is going to be its input capacitance, which is 3 C, divided by the capacitance of a similar inverter. Okay. So, now we are talking that the driving gate is also an inverter. Okay. So, this is going to give me 1, right. So, the logical effort of an inverter is always unity. It sometimes also acts as a reference for me. Okay. And for defining other logical circuits, you can define in terms of the inverter also, taking inverter as a reference. So, we have agreed, we have seen and shown here that the logical effort of an inverter is unity. Now, let us extend this example. There are 2 circuits shown on your slide. Okay. The one on the left, which is outlined in blue, okay. The one which is shown on the left outlined in blue, this is basically a NAND gate, a 2 input NAND gate. The one on the right highlighted in red, this is a 2 input NOR gate. You can see a parallel arrangement of PMOS transistor, a series arrangement of NMOS transistor for NAND operation. Okay. And a series arrangement of PMOS transistors and a parallel arrangement of NMOS transistor for NOR operation. Okay. Now, if I look at the inputs, there are 2 inputs A and B here, and the same inputs are applied here also. So, with respect of each input sees how much unit capacitance. Okay. So, this input which is applied to this PMOS is going to see 2 times C, 2 times the capacitance of a unit transistor, plus another 2 times C from here. Okay. If I look at the NOR gate, this input A is going to see 4 units of capacitance here and 1 unit of capacitance here. Okay. I have written 2 here because we are making the transistor twice the width to compensate differences in mobility. This is a series arrangement. Okay. So, the resistance is going to add up. So, I am going to make one NMOS with half the resistance here, R by 2 here and R by 2 here. When they are connected in series, I am going to get total resistance of R. Because these are in parallel, only one path is sufficient to drive the output to logic high. So, I am going to use width of 2 here. Okay. Here the PMOS transistors are connected in series. So, the net resistance is going to be resistance of this transistor and resistance of this transistor. Okay. And if I add the resistance, this is going to have a resistance of R by 4 plus R by 4, total resistance of R by 2. Okay. And this NMOS transistor has the width same as that of a unit transistor. So, it is going to have a resistance R. So, see again the resistance of a PMOS network is half of that of NMOS network. This is done deliberately to compensate the differences in hole mobility, which is generally lower than the electron mobility. So, coming back to the topic of logical effort, each input in the 2 input NAND gate is going to see a resistance of 2 plus 2, 4 times C. Each input of a 2 input NOR gate is going to see 4 plus 1, 5 units of capacitance. Okay. So, if I want to calculate the logical effort, which by definition is the ratio of input capacitance of the driving gate to the input capacitance of an inverter with same output current. Okay. So, if I am saying for the NAND gate, if the input capacitance is equal to 4 units, okay, 4 times C you can say, okay. C is the capacitance of the unit transistor. We have already seen earlier that the input capacitance of an inverter is 3 times C. Okay. So, that gets divided, you can cancel C and you are going to get the logical effort for a 2 input NAND gate as 4 by 3. Same thing applies for a NOR gate, each input sees a 5 times unit capacitance, okay, divided by the input capacitance of a similar inverter, which is 3 times C. Okay. This is going to give me 5 by 3. Okay. So, the logical effort for a NAND gate, which is 2 input, is 4 by 3, and for a 2 input NOR gate is 5 by 3. In a order to generalize this trend, when we increase the number of inputs, what is the impact on logical effort? Okay. Need to understand, because when number of inputs increases, the amount of input capacitance is also going to increase, and if the amount of input capacitance is increasing, the logical effort is going to change. And as I have said, logical effort is a performance parameter. Higher the value, the worse is the performance of the driving gate. Okay. So, in sometimes when the number of inputs increases by a large amount, it is generally better to divide the circuit into a cascade of smaller logic circuits. Okay. So, similarly for a 3 input NAND gate, each input sees a input capacitance of 2 plus 3 5 units for NAND gate, okay, and for a NOR gate. So, this is a 3 input NAND gate and this is a 3 input NOR gate, okay, and each input in a 3 input NOR gate sees 6 plus 1 7 units of input capacitance, and a similar inverter is going to provide 3 units of input capacitance. So, for a 3 input logic gate, if you are having a NAND operation, the logic effort is 5 by 3 and for NOR gate it is 7 by 3. And to generalize, for an n input NAND gate, the logical effort is n plus 2 by 3, and for a NOR gate 2 n plus 1 by 3. Okay. So, now you can see that as the number of input increases, the logical effort is going to increase quite a lot for a NOR gate. Okay. This is also a major reason why NAND gates are preferred over NOR gates. Okay. This is a frequently asked question, why NAND gates are preferred for logic design over NOR gates. This is one of the reason. Okay. Another reason is related to space and how much the number of transistors required, okay. But this is one of the major reasons that the logical effort for an n input NOR gate is higher as compared to a NAND gate. Okay. So, you can take an example, if n is 10, a particular logic gate has 10 number of inputs. Okay. So, in that case, if n is equal to 10 for a NAND gate, your logical effort is going to be 10 plus 2 12 by 3 4, and for a NOR gate it is going to be 7. Okay. This is only for a 10 input gate, okay, which is fairly easy to find, right, and 10 input is not a very large number for a dense complex VLSI circuit. Okay. So, this is the concept of logical effort. Let us proceed to the other component in the normalized delay. If you remember the equation, normalized delay is G dot H plus P. Okay. So, we have seen what is G, we now need to understand what is parasitic delay. Okay. Parasitic delay is the delay of the gate when the load is disconnected. So, if the driving gate is not driving any load, okay, it is not supplying any, it is not charging or discharging anything, any other capacitance, we say that it is a no load condition. Okay. And to estimate this parasitic delay, in that case we consider the diffusion capacitance at the output node. Okay. So, wherever the output is being measured, okay, and if you disconnect the load, whatever diffusion capacitance is present at that output node, that basically is a measure of parasitic delay. Okay. Again we take the example of an inverter, right, the same inverter which we have analyzed a few times now, right, that has been shown on your slide. So, if you see the output node here X, this is your output node. If it is not driving any load, it has a PMOS connected to it, it has an NMOS connected to it. Okay. So, this PMOS, which has twice the width of an NMOS transistor, okay, it is going to have a resistance, a capacitance 2C, okay, plus this unit NMOS here, okay, the unit NMOS here, okay, is going to have a capacitance C. So, the net diffusion capacitance appearing at the output node is 3 times C, and the resistance being provided is R, okay, because this being twice the width is going to have half the resistance, this is going to have a resistance R. Okay. So, at a time you are going to see a resistance R and capacitance 3 times C. So, the total parasitic delay, which is the RC time delay here, is 3 C times R or 3 RC. Generally, we denote this 3 RC by tau, okay, and we normalize this parasitic delay. As I have said, inverter acts as a reference for a complex logic circuits. Okay. So, this normalized parasitic delay of an inverter is generally taken as 1, because we divide 3 RC by 3 RC, okay, and we get unity parasitic delay. Okay. And if I want to obtain the parasitic delay for common logic gates NAND and NOR. So, this here is shown as a 2 input NAND gate, this is a 2 input NOR gate. We are interested only in the diffusion capacitance at the output node. Okay. So, if you see here in this circuit, this PMOS is connected to the output node, this PMOS is connected to the output node, this NMOS is connected to the output node. Okay. But this NMOS here is actually grounded. So, it is not going to contribute anything to switching delays, because it is grounded, which is a constant voltage. Okay. So, at the output node I am getting 2 times C from here, having width twice, 2 times C here and 2 times C here. Okay. C is the capacitance of a unit transistor. So, if I add it, I am going to get 6 times C, resistance remains R. Okay. So, 6 times R C is the total diffusion capacitance. Okay. So, for a NAND gate, the diffusion capacitance is 6 times R C. Okay. So, the parasitic delay normalized with an inverter is 2 units. Okay. Similarly, for a NOR gate, this PMOS is connected to output node, these 2 NMOS are connected to output node, but this PMOS is not connected. Okay. This is basically connected to a constant power supply VDD. Right. So, for a NOR gate, I am going to get 4 plus 1 plus 1, 6 times RC of diffusion capacitance at the output node. If I want to normalize, I am going to divide by the parasitic delay of an inverter, okay, and I am going to get 2 units. Right. So, in general, the number of inputs decides how much is going to be the parasitic delay in a logic circuit. Right. So, for a 2 input NAND gate, parasitic delay is 2 units, for NOR gate it is 2 units, for 2 input NOR gate it is 2 units, for any n input NAND and NOR gate it is going to exhibit n units of parasitic delay. Okay. So, we have generalized logical effort, we have generalized parasitic delay. Just to take one quick example, we are using linear delay model to estimate the delay of the FO4 inverter. This is a common notation, an inverter driving 4 other inverters is known as FO4 inverter. Okay. If the resistance and capacitance of this unit transistor is given as 10 kilo ohm and 0.1 femtofarad respectively, we assume that the inverter is constructed in a 65 nanometer technological node with tau. Tau is your normalized parasitic delay for your inverter. Okay. So, that is given as 3 picoseconds. Okay. Now, we are talking about inverters, we have seen that the logical effort of the inverter is equal to 1. Okay. The electrical effort is 4, because it is driving 4 other similar inverters of equal size. Okay. The parasitic delay of the inverter is also equal to 1. We are talking about normalized parasitic delay 3 RC divided by 3 RC. So, total normalized delay according to linear delay model, which is D equal to G dot H plus P, is going to be equal to 5 in normalized terms. Okay. And since it is 5, right, the if I try to normalize it, Okay. I multiply it with the normalized value of time delay, which is given as 3 picosecond. Okay. So, the total propagation delay as per this model I am getting as 15 picoseconds. Okay. Normally path delays are expressed in this FO4 inverter delays, this is a common notation, okay, because tau is not a very common notation. Okay. As a general rule, tau can be estimated as 0.2 or 1/5 of the FO4 inverter delay for any respective node. Okay. So, that is the lecture on linear delay model. Just to summarize, we have started with what is known as normalized delay, similar to the equation of a straight line. G is logical effort, H represents fan out and P represents your parasitic delay. Okay. In the next lectures, we are going to continue from here and we are going to go further with the linear delay model. Okay. Thank you.